Rational functions and their graphs. A rational function is a function that can be written as f of x equals p of x over q of x, where p of x and q of x are polynomial functions and q of x does not equal 0. All they're saying is they're putting a polynomial over a polynomial. That's what all those words mean. And they just also say, oh, and by the way, you can't divide by 0, which we've known for many, many years now. That is what a rational function is, all right? The graphs of rational functions, and they've given us pictures of these graphs. They can do all sorts of crazy things. We've dealt with quadratics. Those are parabolas, all right? So we've dealt with some polynomials, but rational starts throwing in a little mix here. You can see that rational functions, we have this little guy here. He just swirls around there. We have this one where they shoot up here, you jump over, you have what looks almost like a parabola here, and then we have this other piece here. And then we have this guy that kind of does this weird thing here. All right, what you'll notice is that while this one is continuous, we don't have any breaks in the graph. Here, we have this graph, and then it looks like we have this completely separate graph right here, and then this completely separate graph right here. All right, and the reason we have that is we have what's called a point of discontinuity. That's just a fancy way of saying a break in the graph, okay? So a point of discontinuity, if a is a real number for which the denominator of a rational function of f is 0, then a is not in the domain of f. We've talked about domain. So remember we've talked about the word domain, and I've said what's the domain? And it's pretty much all the numbers that work except for these. These don't work, okay? And so that's all that's saying. If you have a 0 in the denominator, then that number is outside of the domain because it causes a problem. The graph is not continuous at that point, all right? It cannot be because you cannot define the graph at that point because you're trying to divide by 0. And the function has a point of discontinuity at that point, okay? So all this is saying is when you have a 0, something happens with the graph because all of a sudden you're trucking along fine, then you have a 0 in the denominator and it's like, halt, nope, can't do that, all right? And a couple things can happen. One of the things is they can shoot off like this. All right, but they are points of discontinuity. That's all it is. When you have some type of problem with your graph, like a 0 in the denominator, you have a point of discontinuity. All right, so let's look at these. It says find any points of discontinuity. Well, if I need to find the points of discontinuity, that means I need to figure out where my denominator is 0. So just like on your bell work for numbers 7, 8, and 9, you're going to need to factor that denominator, set it equal to 0, and say these two numbers are going to cause a problem. All right, so for this first one, we got easy factoring going on here. X squared plus 2x plus 1. How do I factor that one? Factors of 1 that add up to 2. Yeah, that's just 1 and 1. If I set that equal to 0, x is going to equal what? -1. So I have a point of discontinuity. And I'm not going to write that out, but there we go. Point of discontinuity at -1. Easy enough. Let's look at the next one. X squared plus 1. How do I factor that? All right, how do I solve though? What do I do? Yeah, subtract 1. I have x squared equals -1. I have a problem. I'm talking about real numbers. What's my problem? Yeah, it would be an imaginary number. And you'll notice that it says it's not a real value, so there is no point of discontinuity here. So none. We have no points of discontinuity here. None. That is going to be a continuous graph. We're not going to have a problem because I can never make that denominator 0. Ever. You can put whatever number you want there. It will never, ever be 0 in the real number world. All right? When it asks for points of discontinuity, that's what it's asking for. Where is there going to be a possible break in this graph? So go ahead and try those 3, A, B, and C. All right, so lots of things can happen with graphs, and it's a little hard to see. So I'm going to scoot some of these out of the way just for a second so I can talk about them one at a time. So we'll just stack them on top of each other. What order do they go in? Here we go. That one, then this one, This one. All right. So let's talk about this guy first. All right. So first, I want to talk about where his points of discontinuity are. If you notice, they give us the little function down here. He's kind of hidden. We have a discontinuity at 1 and -2, right? Makes sense. They are factored for us. The denominator is going to be 0 at +1 and -2. And you'll notice on the graph at +1, we have this little guy right here. And at -2, we have this little guy right here. And this seems to be directing where the graph goes, right? You see that? I mean, it's like the graph gets to that point and gets a little scared and then just runs off, right? And that's kind of what they're doing. Those little dashed lines that they have there are called vertical asymptotes. It is a line that's not actually part of the graph. It shows you where your discontinuities are, or where a type of discontinuity are, called an asymptote. And the graph gets infinitely close to that line but never touches it, okay? Vertical. You have horizontal, and actually they can jump over horizontal, but they get infinitely close to vertical and they never touch it. They cannot touch it because it is not defined there, all right? That is where you have a 0 in the denominator. It's a specific type of 0 in the denominator, and this is what's going to happen to the graph when you have that type of denominator, okay? Something else that can happen. Let's look at the next one that they give us here. So we're going to scoot him out the way, and we're going to look at this guy. Now, this guy also has a 2, right? You can see that 2 causes a problem, but we do not have an asymptote there. What do we have at 2? What happens at 2? It's a hole, actually. Yeah, a circle that denotes a hole, all right? The difference between this guy and the other guy, specifically, is that this guy also has the same exact factor in the numerator. See that? So we have this factor and this factor. So my hole, which is created by that discontinuity, has the same exact factor in the numerator. All right? That's how you know it's going to be a hole. These guys did not have the same factors in the numerator. They were all alone down here. You see that? They were all alone, asymptote. They had something above it that could cancel, hole. All right? And so these are called removable. I can cancel it out. Non-removable. I cannot cancel it out. Discontinuities. They are both discontinuities in the graph. You can see the graph does not touch it, and there's a break in the graph here, right? So I have this little red graph going along. He's all good to go. Then we have a break. We have this graph, good to go. Then we have a break. All right? We have this graph, good to go, and then we have a break. Everybody see that? So they're both discontinuities, but one of them cannot be removed by factoring. One of them can. So if it cannot be removed by factoring, you're going to have an asymptote. If it can be removed by factoring, you're going to have a hole. All right? And basically what happens is when you cancel it, you get y equals x plus 1. Everybody see if I canceled that, I would get y equals x plus 1. Y equals x plus 1 is a linear graph. So your graph is going to look just like what would happen if you canceled it, except at that one little point, you're going to have a hole. All right? And so if you can take it out, it's going to be a hole. If you cannot take it out, you're going to have these vertical asymptotes that it just shoots off next to and goes infinitely. All right, let's look at the other ones that they gave us. This is my next one. Let's look at him. All right. I have a discontinuity. I have 2, actually. I have a discontinuity at +2 and at +1. You'll notice my +2 discontinuity can cancel with the guy above it. Everybody see that? There we have a hole, right? My +1 discontinuity doesn't have anything up here. We have a vertical asymptote. So you can have a graph with both of them, right? One can be removable, one can be non-removable. And that means you're going to have an asymptote and a hole going on with your graph. All right? Let's look at the last one. This looks like you would have 2. All right? X minus 2, X minus 2. All right? So you're like, well, one can cancel, one can't. But you can't have a hole and an asymptote at the same point. That does not make sense. So if it looks like it's going to cancel and remain, and it's the same exact discontinuity, it's going to create a vertical asymptote. All right? It's going to create a vertical asymptote. So everybody see that? All right, So even though one of those can cancel, you still have one left over that cannot cancel. You're going to have that vertical asymptote there. All right? The rational function, and that's just a function over a function, has a point of discontinuity for each real zero of q of x. So every time q of x is 0, you're going to have a discontinuity. Every time your denominator is 0, you're going to have a problem. If they don't have any common real zeros, then it has a vertical asymptote. If they do have a common real zero, there is a hole in the graph. So this is what it's telling you. Common. If the numerator and denominator have a common factor, right, that can cancel, that cannot cancel out, they have no common factors, then you have a vertical asymptote. If they do have a common real zero, meaning the top and bottom can cancel, then you have a hole in the graph. All right, hole in the graph. So let's look at example 2. Example 2. Describe the vertical asymptotes and holes for the graphs of each rational function. So that they want to know, list the discontinuities, but be more specific. Tell me what type it is, okay? Tell me what type it is. All right, and so we do this. We say, well, the denominator is going to be 0 at x equals 2 and at x equals 3. Are either of those able to be canceled? No, they are not. So they are both what? They're both vertical asymptotes, right? All right, let's look at the next one. Where's my discontinuity going to happen at? 2. What type is it? It's a hole. All right, let's look at the third one. Discontinuities, where do they happen? At x equals 3 and x equals -4. What are they?
Vertical,
Asymptote? That's 3, right? Because it's cancelable, but you still have that guy left over, so he's vertical. Yep. And what about -4? That's a hole. All right. At most, you have one horizontal asymptote. That's not true of vertical. You can have many vertical. We've actually seen that, right, where you can have multiple vertical asymptotes. It can have many undefined on the denominator, all right? But for horizontal, you have at most one. They give you all this verbiage here, and I'm going to give you the shortcut in layman's terms. But the graph of a rational function has a horizontal asymptote at y equals 0 if the degree of the denominator is greater than the degree of the numerator. If the degree of the numerators are equal, then it's at y equals a over b, where a is the coefficient of the highest term in the numerator, b is the highest term denominator. If it's greater in the denominator, numerator than denominator, it has no horizontal asymptote. Lots of words, okay? Basically, you're going to always look at your degrees. All right, so if I give you this example, let's say I have like 2x squared minus 3 over 3x cubed plus 2. All right. And then I have 2x cubed minus 3 over 3x cubed plus 2. And then I have 2x to the 4th minus 3 over 3x cubed plus 2. The only thing that changed are my degrees on top, right? So the first situation, the degree of the denominator is greater than the degree of the numerator. That's my first situation here. So I'm looking at degrees. Don't forget what degrees are. Degrees are my highest exponent. Now keep in mind, sometimes they'll throw you for a loop and they won't put it in standard form. Okay? That's okay. Degree is the highest exponent. So my degree of my numerator is 2. My degree of my denominator is 3. Okay? If the degree of your denominator, let's write it not in that, there we go. Degree of the denominator is bigger than the numerator. That's the situation here. the denominator is bigger than the numerator, you're going to have that horizontal asymptote at y equals 0. Remember, it's a line. Y equals 0, which is actually your x-axis, right? Y equals 0 is your x-axis. Let's say they're the same. Degree equals of the numerator equals the degree of the denominator. They equal each other. All right? When that happens, you use your leading coefficients. Okay? Leading coefficients in rational form. So I am going to have a horizontal asymptote here at 2/3. Leading coefficients, the number's in front of my highest exponent, and it's just going to be a over b. It's that fraction, all right? And then the last scenario is that the denominator is smaller than the numerator. So my numerator is larger. I don't have one. I do not have a horizontal asymptote if that happens, all right? Those are your shortcuts. So it's really easy. You literally just look at the degrees, okay, to figure out what's going on with it. So when you start sketching these, which we're about to do, I ask for all these things. I'm like, where's this? Where's this? Where's this? The first thing I usually look for is my horizontal asymptotes, because after that, I'm going to start factoring it. So I want to use my original to talk about my asymptotes, because once I factored it, then you have to think about what your degree is. So let's look at example 3 here. What are they? It's very simple. Find it. What's my degree on top? What's my degree on top? My degree is 1. What's my degree on bottom? My degree is 1. They are the same. They will have one, and it's going to be at 3/1. So y equals 3. Easy enough? Let's look at this guy. What about the degrees? They gave us all of the same example. They didn't give us any other ones. Oh, goodness. These are the same. So it's y equals what? -2. These are the same. Y equals 2. They did not give you any ones that don't have any ones. So x and y intercepts. X-intercept occurs when y equals 0. Okay. Y-intercept occurs when what? X equals 0. All right, so quick note. When y is 0, that means your numerator equals 0. Okay? The only time it's not going to be an x-intercept is if it's also a whole. Okay? Everybody hear me. Because remember, when your numerator is 0, if it's the same 0 as the denominator, that means it's a whole. Okay? Everybody remember that? Okay? So the y-intercept isn't affected by that, but your x-intercept can be affected by wholes. So it's not going to be an x-intercept if it's already a whole, because we're just saying it can't be an intercept and actually cross the graph if it's a whole. We've said it can't be that. Okay, that doesn't make sense. So as you go through these, I'm going to ask for several things on these graphs. I'm going to ask for x-intercept, y-intercept, vertical asymptote, horizontal asymptotes, and wholes. All right, and then I'm going to ask you to sketch the graph. That's what these look like on a quiz or test, okay? So typically what I'll do is I'll go through and I'll do some of the easy ones that don't really require much thinking, right? I will not give them to you already factored. So very often you want to do what you can do before you factor, which is often finding the y-intercept, plugging in a 0, and finding your horizontal asymptote. Those are easier before they're factored, okay? So normally you would get this when it looked like this, x plus 2 over x squared minus x minus 12, something like that. Everybody see that's what that would be? Hopefully I did my foiling right. And so this is how you'll be given the problem. And so typically if I were having to find all 5 of those things, I would say, well, let's see. My horizontal asymptote is easy to find because I can easily see what? My degree on bottom is bigger. What did we say happens if my degree on bottom is 0? Where do I have a horizontal asymptote? At y equals 0. All right. The other thing that's easy to find when it's like this is y-intercept. Because I basically get 0 plus 2 over 0 minus 12. Everybody see that? See why it's easier to do that then? It's 2 over negative 12. That's my y-intercept. Because when I plug in a 0 for x, I'm going to get negative 1/6. Everybody see that? See why that's easier to do before I factor it? Yes? Very simple. All right. Then I'm actually going to go to factored form, and I'm going to decide if I have horizontal and vertical asymptotes. Okay? I mean vertical asymptotes and wholes. All right, so let's look at discontinuities. So we're going to look at vertical and possible holes. I have discontinuities at -3 and +4. Everybody see that? Are either of those removable? No. So they're both what? Vertical. So x equals -3 is vertical. X equals 4 is vertical. Nothing is removable. I have no holes. Which means anywhere that my numerator is 0 is going to be an x-intercept. Everybody see why I did it that way? If I go ahead and establish what's happening with my numerator, then I can decide if it's going to be an actual intercept. If that x plus 2 on top had canceled, then I wouldn't have any x-intercepts because the only possibility of a 0 would be my hole, right? So now that I know that, I can say, okay, well, for x-intercept then, where my numerator is 0, that's going to be -2, 0. That's an x-intercept, okay? So I have everything I need to sketch this graph, okay? I sketch it by putting out my vertical and horizontal asymptotes first, okay? And so I am going to do this process. I'm going to sketch those dotted lines that are just going to help me graph this guy. So here's my horizontal. All right, I have some vertical at -3 and +4. So I'm going to go to -3 here. If we can get him a little bit straighter. There we go. -3 right here. +4 goes right here. Okay. Then I'm going to put in my intercepts, x and y intercepts here. This is where you can have a potential situation where it crosses, by the way. And we'll talk about that. So we have an x-intercept at -2, 0. Yes, that's a horizontal, but that's actually going, remember I said it can cross over the horizontal, all right? We have a y-intercept at 0, -1, 6, so we know we're going to cross there, all right? So we know that our graph is going kind of curved right here. So I know that it's going from here to here, and it can't touch that guy. Everybody see that? He cannot touch the vertical. So the only thing he can do is go infinitely right here, because he's not allowed to touch that vertical at all. He's also going this direction, and we know he's going to get infinitely close to him somewhere and shoot down. We're sketching, so it doesn't have to be perfect. All right? So everybody see that? So those two are going to help me figure out what's going on somewhere on the graph. Now I just need to figure out what's going on this side of the asymptote and on that side of the asymptote. All right, so then I have to determine what's going on either side of these. The best way to do this is just pick a number and see where he is. Because he's always going to do this kind of crazy L loop there. He's always going to do that crazy L loop right there. We know it doesn't cross. Why doesn't it cross? Because we only have one x-intercept, and we've already established where he is. So I know if I can figure out where it is over here, it's not going to cross over this because I don't have any more x-intercepts. I only had one, and I've already figured out where he is. So I know that if it's on either one of these, it's just going to shoot off infinitely to that asymptote, infinitely to that one, if I can just figure out what side of the graph it's on. So if you pick a number, let's say -5, and plug it in, you just got to figure out what's going on. So I'm going to do that. I'm going to pick a number. Let's say -5. It doesn't matter which one. -5. What happens when I plug him in? -5 plus 2 is going to be a negative number, right? Yeah, and you don't have to worry about what it is. But yeah, it's a -3. All right, so it's negative on top. -5 plus 3, is that going to be positive or negative? Negative. -5 minus 4 is also going to be. Am I going to be in the negative side of this or in the positive side of this when it's all said and done? Negative. Negative over a positive is a negative. So I know I'm going to be down here in negative territory. Everybody see what I did? I don't even care what the numbers are. I'm just trying to figure out where he is to sketch it. Okay? I know he doesn't cross over this. And the reason he can't cross over that is I've already crossed over it, the only place it can cross over. Okay? He has already crossed over my x-axis, the only place that it can. So I know that it's going to go infinitely somewhere here. I know he can't touch this guy, so it's got to go. This is how it has to go if it can't cross over the x-axis and it can't touch my vertical asymptote. It has to do that. It will always do that. okay? So now I just need to go to the other side and figure out what it's going to do on that side. So you're basically taking a chunk at a time. We figured out what the middle does by my intercepts, okay? We figured out what this guy does by just picking a number and figuring out if it's in the positive or the negative. So we're going to do the same thing here. Positive 5. What happens with positive 5? Well, positive 5. Positive 5 plus 2. Is the numerator going to be positive or negative? Positive. Positive 5 plus 3. It's going to be positive. Positive 5 minus 4. All right, so this guy's going to be up here. We know he cannot touch this guy because we've already crossed over the only place that we can. We know it can't touch this one because it's a vertical asymptote. So it's going to look like that.